Welcome to sitza.com. Hydration of alkenes. We can add water to the alkenes to get alcohols, right? And this is an electrophilic addition reaction. So when you have an alkene, you can add water in the acidic medium. The mechanism here in this case will be electrophilic addition reaction, and in the water, we get H plus and the OH negative ion, right? And it is the H positive ion that will attack on a carbon-carbon double bond, because alkenes are more reactive due to the presence of pi bonds, and pi bonds can be attacked by the electrophiles. All right, so when you have alkene and you add water in acidic medium, what happens? The carbon-carbon double bond breaks, and one carbon gets a hydrogen, the other one gets a OH group, so you get alcohol. And the addition will always be, in this case, the Markovnikov rule, right? So it follows the Markovnikov's addition, and according to the Markovnikov addition, hydrogen is added to the double bonded carbon with more number of hydrogens. Okay, I'll repeat it. According to Markovnikov's rule here, right, the hydrogen will be added to the double bonded carbon that has more number of hydrogen atoms. So you have two hydrogens here, and this carbon doesn't have any hydrogen, right? So that means this hydrogen will go here, and the OH will be added to this one. So in that case, what you will get? You get a product like this: CH3C, CH3. First attack is from the electrophile, and it will go into the CH2, and it will convert the CH2 into CH3. Now you have a single bond, and this OH will be over here. Correct? This is the product that you will get. And if you look at the mechanism, again, what is the mechanism? Mechanism is, the first, there will be an attack of electrophile on the carbon-carbon double bond, and this carbon, this electrophile will go to this CH2, right, as per the Markovnikov's rule, right? And you get what? You get a carbocation like this: CH3C, CH3, and this is, now this was the CH2, and it will be now CH3, right? And the pi bond shifts actually in this direction. It forms actually a bond. These pi electrons, they shift towards the electrophile. All right, so you get a carbocation over here. Correct. So that means these pi electrons, they are used to form a bond between the carbon and the hydrogen. All right, between this carbon and the hydrogen, and therefore this particular carbon, it gets a positive charge. That means the intermediate that you get here is carbocation. Right, you get a carbocation. And then in the next step, what's going to happen? The next step will be the attack of a nucleophile, which is here a hydroxide group. So it is going to attack on this one, and you get this product. Now see, what if you have anti-Markovnikov addition? Suppose if this addition, if this hydrogen doesn't go to here, right? What is the reason for the Markovnikov's rule? Why the hydrogen should go here? Because the intermediate here will be the tertiary carbocation in that case, right? In this case, it is a tertiary carbocation. However, if this electrophile, suppose, if the first attack from the electrophile, it goes to this particular carbon, right? It forms a bond here, the carbocation will be here. In that case, what will be the other product? The other product will be CH3, C, CH3 here, and this carbon gets one more hydrogen here, right? And then you will have a CH2 and the positive here, right? This is the carbocation. And we know, this particular carbocation is a primary carbocation, right? And this one here is a tertiary carbocation. What is the order of stability of the carbocations? The order of stability of the carbocations is tertiary is more stable than secondary than primary, right? Okay, so that means when the addition follows the Markovnikov rule, that means you get a tertiary carbocation, which is more stable carbocation. And if it goes here, what you will get? A less stable carbocation. All right, so that means preferentially, this electrophile likes to attack on this carbon rather than this, right? Why? Because you get a more stable carbocation. All right, so that means the hydration of the alkenes produces the alcohols, and the intermediate there is a carbocation. Right, let's take a couple of more examples here. Again, you see here we have a carbon-carbon double bond, and this particular carbon has one hydrogen attached to it, and this one doesn't have. Right, and if you add a water here, what will happen? The hydrogen H positive is going to attack. It will be with this carbon, and the OH will go to this particular carbon, right? OH negative in the second, stuff will attack on this carbon. So Markovnikov addition again here. Hydrogen is added to the double bonded carbon with more number of hydrogens. This carbon has one hydrogen, this doesn't have any hydrogen, right? Okay, so therefore you get a product like this: CH3, CH3, CH2 now, and the CH3, and you get OH here. Correct. Again, you will get what? You will get an intermediate. A carbocation will be the intermediate. Now let's take another example here. You have a carbon-carbon double bond, and this particular carbon has two hydrogens. This carbon over here doesn't have any hydrogen because it is attached with other two carbon atoms, right? So therefore, the hydrogen H positive electrophile, it will be added to this carbon, and the OH will go here. So the product will be like this. You get OH here, and this will be the CH3, right? And again, what is the intermediate? The intermediate will be the carbocation here. So let's take another example. A molecule like this, if it is, a CH3 here, and then you have a CH, a double bond CH2. And now if you add the water here in the acidic medium, what will happen? See again, what will be the first step? The first step will always be there that, the electrophile will go to this particular carbon, right? Because this is the CH2. The double bonded carbon with more number of hydrogens gets one more hydrogen, right? This is what we have learned, as per the Markovnikov's rule. So that means the H positive will attack over here, and the carbocation will be formed here. So you will get here a carbocation. You have a single bond, carbon, hydrogen, and a positive charge over here, and this will be the CH3 now. All right, this will be the CH3. Now see, if the nucleophile attacks here, the OH attacks here, what will be the product then? If this nucleophile attacks on it, what will be the product? The product will be CH3, CH, CH3 here, and the CH, OH, and the CH3 here. Correct? This will be the product here. But what happens in this case? This example is a little different than the previous one. Here in these examples, the previous examples, we have seen that there wasn't any kind of a possibility for the rearrangement of the carbocation. But here in this case, the carbocation rearrangement will take place. Why? Because the carbocation that you get here is a secondary carbocation, isn't it? This particular carbocation is secondary carbocation. But if you shift this carbocation, this positive charge over here, it will be a tertiary. And how is that possible? This can be possible when the hydrogen along with both electrons, it will shift to this carbocation. Right? When it shifts to that, this is what you call as a hydride shift, right? H negative shift. Hydride shift will be there. So when there is a hydride shift, you get a carbon here with a positive charge. You get a molecule like this, CH3, C plus, CH3 here, and the CH2 now, and the CH3. Look at this one. This is a tertiary carbocation, right? This is a 3-degree carbocation here, and this was a secondary carbocation. And the reason why there will be the hydride shift, what is the driving force for this hydride shift? It is this extra stability of the carbocation, right? Because we know the order of stability of the carbocations is tertiary is more stable than secondary than primary, right? So that means the carbocation, if you get a secondary, it can rearrange to the tertiary if there is any possibility, right? You have to look at the molecule, if you can rearrange it to the other stable carbocation. And the rearrangement of the carbocation is very common there, right? Wherever you see the carbocation, there will be some possibility of the rearrangement of that carbocations. And remember, always the stability will be, the rearrangement will only take place when you have a secondary and it can go to the tertiary. A rearrangement is not possible from secondary to the primary. Correct? So less stable carbocation can rearrange to a more stable carbocation, right? So basically then, what will be the other product? The other product will be, when the nucleophile attacks on this one, right? It's going to attack on this one. What you will get? You get a CH3, COH, CH3 here, CH2, and the CH3 here. So basically you get two products, A and the B here, right? You will get two products, but which is the major product, right? The major product is from the more stable, the carbocation, that is from the tertiary. So this will always be the major product, and this is the minor product here. Correct? Hope you got the concept. Thanks for watching the video. Bye for now.